All right, I'll do that. So this workshop is on the hyperreal numbers. So we'll start with what the hyperreal numbers are, and then we'll work through to an application of the hyperreal numbers to a test for series, for convergence or divergence of series. So I'm making the assumption that most, or at least a good number of the individuals that are in this workshop have little to no experience in the hyperreal numbers. So we'll start from the very beginning, and we'll look at a definition of an infinitesimal. So a number h is infinitesimal if either it's positive, but it's less than every positive real number, or it's negative, but it's larger than every negative real number. Now we know there's no smallest positive real number, right? But then we're looking at an infinitesimal as a number that is less than all of these positive real numbers. So it's not a real number. So it's one of what we will call the hyperreal numbers. So I'll let little omega be a positive infinitesimal. That means it's greater than 0. But if it's infinitesimal, it's going to be less than r for every positive real number r. So it's less than 0.0073, less than 0.00000000314. It's less than 10 to the negative 2,754,658, and so on. So in other words, it would have to start, if you look at its decimal representation, it seems like it would have to start with infinitely many zeros. So an interesting idea. But if you give me an infinitesimal and I double that infinitesimal, is that number 2 omega still infinitesimal? So one of the things that I'm wanting for our workshop today is for it to be very interactive. And so I'll ask these questions, and especially for the students, if you would like to answer one of these questions, go ahead and unmute yourself and chime in. So, and we can have multiple people chiming in too. That's great. So would twice omega be an infinitesimal?
No.
Okay, I hear one no. Anyone for yes?
Depends on how we define 2 times omega.
Okay, very good question. So if we're going to look at 2 times omega, so let me change the way I'm sharing my screen here. Okay, so let's see, I've got to put that down and I've got to get that down. Okay, here we go. So can you see now both my pad of paper and the slides?
Yes.
Yes.
Okay, very good. So the question was then, well, how would we define 2 times omega or omega plus omega? So the idea would be that our arithmetic would work the same way it does in the real numbers. And there's something that's very sophisticated behind this called the transfer principle. But as you recall, when you define things like the complex numbers, you want all of your arithmetic to work the same way that it does in the real numbers. So your arithmetic and your algebra, etc. And so we'll make the assumption that our arithmetic and algebra all works the same with any of these hyperreal numbers that it does with the real numbers. So if your 2 omega, well, if omega is less than any positive real number, would 2 omega also be less than any positive real number? So anyone want to answer that one?
I think it's still infinitesimal.
Right. It would still be infinitesimal, because if it wasn't, then 2 omega would be bigger than some real number r. So omega would be bigger than half of r, and that would be a contradiction. So then how about 48,573.6 pi times omega? So would that also be infinitesimal?
Sure.
I believe it would be.
All right. Or any other real number multiple of omega?
Yes.
Okay. Now here, there's actually one exception. If you look back up here to our definition, 0 is not an infinitesimal. Now, some other sources will go ahead and say that 0 is an infinitesimal. In the system that I'm using here, 0 is not considered an infinitesimal. So, okay, 0 is a real number, so 0 times omega would be 0, but with that one exception, it would be true that any other real number multiple of omega would be infinitesimal. So if we're going to learn new numbers, think back to your experience in the past. One of the things you would do is figure out where those numbers fit on a number line. So where do you think these infinitesimals would have to fit on a number line? So could they fit to the right of 0? Or to the left of 0? Or how far? The problem is that if you try to squeeze them any real number distance to the right of 0, then it's over here with the real numbers. It's bigger than some of the real numbers, or less than some of, or sorry, or less than some of the negative real numbers. So it's like a portal into another world. If you have all of these real number multiples of this omega, they really would all have to fit into the number line right here at 0. So you can think of this like in a video game. There's a portal to another world here at 0. There's this entirely new level of your video game called the omega level that's below 0. But then that brings us to another interesting question. Where do you think omega squared would fit on a number line? Would it fit on the omega level line?
Sure, they'd have to be close by the same premise, right?
Right. So would they be close to omega or negative omega? So here the principle is that omega squared would be omega times omega, right? So your omega times omega would be less than 3 omega. It would be less than 0.007 omega. It would be less than 10 to the minus 48th omega, because omega is less than each of these real numbers. So that means that this would, omega squared, would be infinitesimal compared to omega. So we have even lower levels. So your omega squared level, the omega squared would fit on a separate level below the omega level, because all of these numbers would be infinitesimal by comparison to little omega. And same thing then with an omega cube would be even lower. And so you get this infinite collection of levels of numbers, of number lines that are below the real level. And you could even have some in between, like omega to the power of 1.5 should be in here somewhere, or square root of omega would be right in there. So you'd have infinitely many levels, in fact, between each of these levels. So it becomes a very rich structure of these numbers. Okay, but now instead of just looking at infinitesimals, let's look at their reciprocals. So if something is infinitely small and you take its reciprocal, how large do you think that would be?
Pretty big.
Okay, yes, pretty big. Right, because if little omega is less than 1/1000, you can take reciprocals and that changes the direction of your inequality, right? So 1/little omega would be bigger than 1000, or bigger than 1,000,000, or bigger than 10 to the 497th. So if I call this 1/little omega a capital Omega, then it's larger than any real number, so it's infinite. It's infinitely large. So these hyperreal numbers contain numbers that are infinitely large as well as infinitely small. And by the way, little letters for little numbers like omega for an infinitesimal, capital Omega, big letters for big numbers. So that's the scheme. So just remember that little omega and capital Omega are reciprocals of one another in this scheme. So where would that fit? Well, we had our real number line here. Well, your capital Omega would be infinitely large. So a real number is infinitesimal in comparison to something that's infinite. And so the real level would then fit right in here at 0 on the capital Omega level. And you can keep going to higher levels of numbers. And again, infinitely many different levels between each of these. Like your square root of omega level would fit in between your real level and your capital Omega level. So you have infinitesimals, you have infinite numbers, and they can all fit on a number line, but just on various levels, lower and higher. So we need a definition of what it means for two numbers to be on different levels or on the same level. And so if you have two hyperreal numbers, the idea is that the number A is on a lower level than B if A over B is infinitesimal. So if the numerator is on a lower level than the denominator, then it's like this is much, much, much smaller than the denominator, so it would be infinitesimal. But if you revert, you can reverse it. If A is on a higher level than B, then B over A would be infinitesimal. Or you could say that A over B is infinite. Or they're on the same level if it's approximately a real number when you take the quotient. All right, so here's my question for you. Are the two numbers on the same level? Or if not, which one is on a higher level? So someone unmute yourself and give an answer. 47.2 or 98,475 omega?
They are not on the same level.
Okay, so which one's on a higher level?
47.2.
All right, then 47.2 or 0.004 capital omega, which one is on the higher level?
Is it 0.004 omega?
Right, because that one's infinite. Okay, now how about the number of dollars in the US national debt or an infinite number capital omega?
Omega.
The
Or
debt.
omega is the higher on the higher level.
Yeah.
We hope so, but there may have been a little hesitancy on the part of some on answering that one. Okay, 12 capital omega squared or omega cubed?
I would think that it's omega cubed because each level is strictly higher than the previous.
Correct. So the larger the exponent on capital omega, the larger the number, the higher the level it is. Okay, how about natural log of omega or natural log of omega squared? Okay, that
Properties of natural logs, you can move the 2 out in front of it, but I don't know what that means.
So it would be, so natural log of omega squared would be twice natural log of omega. And therefore it would just be twice this. So it would be on that same number line. So 1 times natural log omega, 2 times natural log omega, 3 times natural log omega, etc. It would be on that same number line. Or by that definition we had before, if you take natural log omega over natural log omega squared, you would get 1/2, which is a real number. So if you get a real number when you take their quotient, then they would be on the same level. All right, so next we have a partial picture of levels of hyperreal numbers. So I showed you so these are, by the way, the infinite levels of hyperreal numbers. So you've got your real number level, you have your omega and then the powers of omega that are larger than 1 or smaller than 1, right? Like omega to the 1/2 to the 1/3 to the 1/4. It turns out that the natural log of capital Omega is below every one of these levels. And then natural log of natural log omega is below that, etc. Exponentials are above all of your powers of omega, above those levels. And this might remind you of big O notation and the idea of rates of growth of functions. That exponential growth is faster than polynomial growth, faster than root growth, which is faster than logarithmic growth, which is faster than log or log growth, etc. So again, this gives us an idea of the rates at which things grow. All right, so now let's look at approximation. When you look at your calculator and you do square root of 2, you don't write down all the decimal digits of square root of 2 because there's infinitely many. You'll just say, okay, that's 1.4142. Well, they're not exactly equal though, really, right? So you might write square root of 2 is approximately equal to 1.4142. And you could find the error in that approximation or your percent relative error. And all of these are real numbers. That error in the approximation of square root of 2 being 1.4142, that's a real number. The percent relative error is a real number. But what if we were to approximate something like a real number plus an infinitesimal? That's infinitely close to that real number 7, right? So the approximation 7 plus omega, as approximating that as 7, should be really pretty good. And in fact, if you're looking at this as in decimal form, you would have infinitely many zeros at the beginning of your error or percent relative error. And that relative error then is infinitesimal. So it's a very, very good approximation. So you can define what it means for two numbers to be approximately equal, that x is approximately equal to y if that relative error is 0 or infinitesimal. Now you have to have x not 0 for that definition to work, and then 0 is approximately equal to itself. And it turns out then that if you have a number that's on a lower level than another number, you can throw it away when you approximate, like the 7 plus little omega is approximately 7. So we can throw away lower level terms just be careful to know that the terms truly are on a lower level. We're skipping some important details today. But you can also approximate a fraction by approximating numerator and denominator separately. So that's important. So let's approximate these quantities. So capital omega plus, what would that be? 12 billion. So an infinite number plus a large real number. What would that be approximately equal to?
Omega.
Yes, it would be approximately equal to capital omega. What about capital omega squared plus capital omega cubed? What would that be approximately equal to?
Omega cubed.
Yes. Now it seems weird to throw away something that's infinite like the capital omega squared, like it's nothing. But Congress does that when they throw away billions of dollars all the time, right? So well, that's not throwing away something infinite, but it sure seems that way.
Is that because these numbers are dense?
Well, it's because the numbers, we have different relative sizes of these numbers. And so whatever number you have, like something infinite, like your omega squared, you can have something that's even infinitely larger than that. So it can be, so then it's infinitesimal by comparison, one can say. So what about this next one?
E to the omega.
And that's correct, because those exponentials were on higher levels than the powers of omega. And we could even do fractions like this one. Does anyone want to take a stab at that one?
Omega.
Okay, I heard two people at the same time there, I think. So 3 capital omega. Now, it is legal to approximate under a square root, so that denominator is approximately square root of omega to the 6th, which would be omega cubed. And then you get 3 omega, or your capital omega, when you're done. Okay, what about this final one?
$39.6.
Right, because the other numbers here are infinitesimal. Now I want to show you a picture of approximation. So the idea is that on your real number level at 39.6, if you were to add any infinitesimals, those would be on a level below that. So let's look at the omega level below this number. So it's like every single number is a portal to another world below it. So you would have a number line of 39.6 plus infinitesimals on the omega level. So you can add little omega, twice little omega, 3 times little omega, etc. So 39.6 plus 2 little omega would be here. But then to add a little omega squared to that, you have to go to an even yet lower level than that. So one idea of approximation is to take whatever your number is, like your 39.6 plus 2 omega minus a little omega squared, and rise up in these levels to the highest level you can without going to 0. So on an infinite level, this would go to 0. So this is the highest it could rise to, and that's where the approximation is. Okay. So that's a little bit about some of these approximations then. Now let's go into the mode of looking at test for series. So I know that many calculus students love series, sequences and series, right? Well, it is one of the more challenging topics. And you had many different tests for series, like you could look at geometric series. You had a test for divergence, an integral test, a p-series test, a comparison test, and many more. But what are we actually trying to do when we're testing a series? Let's think about the sum of 1 over n versus the sum of 1 over the n squareds. You can graph the first few terms, And the idea is that the harmonic series 1 over n is going towards 0, but at a fairly laggardly pace. It's going towards 0 slowly enough that it has time to accumulate as large as you wish. But the 1 over n squared, that's a p series with p equals 2, bigger than 1, so it converges. That one's going to 0 fast enough, or the terms of that series are going to 0 fast enough that it doesn't have time to accumulate much, and so that will stay finite. So the real question then is, how fast are the terms of a series going to 0? If they're going to 0 slowly enough, it can still diverge. Fast enough, it must converge. And really, all of these series tests have a method for measuring how fast the terms of a series go to 0. For a geometric series, it's the common ratio R that measures how fast the terms are going to 0. So if absolute value of R is less than 1, it converges, greater than 1, it diverges. Right, your integral test. Does the series go to 0 at the same rate as the integrand in a convergent or divergent improper integral? Or the comparison test. Do the terms of the series go to 0 faster than some other convergent series or slower than some other divergent series? So each of these series tests are trying to measure how fast the terms go to 0. So I claim we can use the hyperreals to build a comparison test, a level comparison test, I'll call it, that can be very simple to apply and very or nearly universal. So we will do this with series with positive terms, though, by the way. So we already had that slide earlier where we looked at levels of infinite hyperreals, and I mentioned how they can compare rates of growth for functions. The question is, can we use those same levels to judge how fast the terms of a series are going to 0? So one idea would be to use the omega term, A sub omega. So in other words, instead of use the 100th term or the millionth term or the trillionth term, let's go infinitely far out into the sequence and see what such a term would look like. So if you are looking at sum, n goes from 1 to infinity of 1 over n, your omega term would be 1 over capital omega, which is infinitesimal. Or if you're looking at sum n goes from 1 to infinity of 1 over n squared, which this one we know converges, you would have a sub omega is 1 over capital omega squared, so an infinite term out here. So 1 over, well, a term with infinite index, so infinitely far out in your sequence. And that would be little omega squared. That's also infinitesimal. But when we are looking at our rates of growth, we are thinking of those as like your infinite levels. And so let's instead use the reciprocal of these. So instead of looking at the omega term, let's look at 1 over a sub omega. So 1 over capital omega, which is capital omega. Or this one, 1 over, so this is 1 over a sub omega. So 1 over omega squared, which is capital omega squared. Now, when we looked at our chart with levels of hyperreals, we saw that omega squared was on a higher level than capital omega. So maybe if terms are going to 0 real fast, like these up here, your series could converge. Or slowly enough towards 0, they might diverge. So ones that we know would work, your harmonic series, if you do 1 over a sub omega, you would have capital omega, that one diverges. And for the sum of 1 over n squareds, you get capital omega squared, and sorry, that one converges. Okay, so the question then would be, if we know the convergence and divergence of our series, can we mark our rates of growth chart according to diverge or converge? Okay, so students, tell me another series like your harmonic series or sum of 1 over n squareds. Tell me another series that you know converges. Okay, or faculty, you can chime in too.
1/2 to the n power.
Okay, 1/2 to the nth power. All right. Well, if you do 1 over a sub omega on that one, that would be 1 over 1/2 to the power omega. And do your arithmetic, that's 2 to the power capital omega. Now, this one, of course, is a geometric series with r as 1/2, so it converges. So we'll mark 2 to the capital omega as converges. So it seems like there's a divide here with converges up here, right? Your P series, geometric series with R greater than 1. Down here, you would have P series with your P less than 1, and those diverge. So it seems like there's this divide between converges and diverges. Okay. So for time's sake, I want us to go ahead and go through this next slide fairly informally. That suppose you have a convergent positive term series, like one of these, and you have another positive term series for which, when you do this 1 over a sub omega, it's on a higher level than 1 over c sub omega for every positive infinite hyperreal integer capital omega. So for all of the infinite terms in your series. Then it's kind of like the comparison test, because these numbers are larger than those numbers. So that means in your reciprocal, the terms of this series are smaller than the terms of that comparison series. Now, there is a little bit of non-standard analysis that's needed in order for that to, to prove that. And so it has to do with internal and external sets, but we can skip that, those details. But it turns out that the comparison test would apply and this series would converge. So if you know that one of these levels has, you have a sequence for which 1 over a sub n gives you one of these, anything else that gives that to you or higher will converge. Or same idea with diverge. And that's going to give us then convergence and divergence zones. So anything where 1 over a sub omega gives you one of these levels is in the convergence zone, and your series will converge. Down here, these are in the divergence zone, and your series would diverge. So keeping this picture in mind, we have the level comparison test. So if you give me a series with non-negative terms, all I have to do is take 1 over a sub omega, and if it's in the convergence zone, then the for every one of these omegas, if it's in the convergence zone, then your series converges. In the divergence zone, then the series diverges. So it's a very simple test to apply. So let's take a look at some series and see if we can figure this out. Okay, so students, if you have a piece of paper and pencil with you, take a look at that series, sum of the n squared plus 4 over 5n cubed plus 8. the 1 over a sub omega term, where these are your a sub n's, would be 1 over omega squared plus 4 over 5 omega cubed plus 8. Now, we can approximate this, right? You can approximate these things by approximating numerator and denominator separately. So your capital omega squared plus 4, like we were doing earlier, would be like your capital omega squared. In the denominator, that's approximately 5 capital omega cubed. So that would give you 5 omega cubed over omega squared, which is 5 omega. So it's on this omega level. And then you can come over to your chart and say, okay, that one diverges. And you would conclude that it diverges. So there are a couple more there. I'll give you a moment to look at those next two series, and someone let me know whether you think those converge or diverge. I guess it's easier if I have the chart there. Okay, folks may have had a moment. So on that one in the middle, you would have 1 over your omega squared minus 3 omega divided by cube root of omega to the 10th minus 4 omega squared. But when you approximate, you can get your omega squared over cube root of omega to the 10th. So that's going to give you your omega to the 10^3 over omega squared, or omega to the power, let's see, what would that be? 4/3. So that one converges. And the last one, you would wind up with a 4 to the omega over 3 to the omega, which is 4/3 to the omega. And that's also up here in this convergence zone. So we could try to play Stump the Test. So faculty members, do you have a challenging series with positive terms that we could try to see if this level comparison test can handle it? Anyone want to chime in? You'll have to unmute yourself.
I don't know if it's challenging, but would you do the Taylor series?
Okay. For a Taylor series, we could look at something like some of the, let's just do, say, x to the n over n factorial, say. You could do something like that. Now, you would be trying this for an individual value of x, right? For each individual value of x, like you would with the ratio test. So then your 1 over a sub omega would be omega factorial over omega, or sorry, x to the power omega. But it turns out that your omega factorial is in between these exponential levels and that omega to the omega level. And it's certainly going to be higher than any of these. This is where your x to the power omega would be. And so you can say that's going to be, well, you could do a little bit of algebraic manipulation and say that's going to be on a level up here in the convergence zone. So that one converges for all values of x. It turns out that the ratio test is more convenient to use if you're looking for your intervals of convergence, but it can apply to something like a Taylor series. Okay, anyone else want to play one with a stump the test?
Sure, I got one.
Okay.
Absolute value of
Okay.
sine of 1 over x.
Okay. Or 1 over n. Okay, so the sum of absolute values of sine of 1 over n. Okay, so your 1 over a sub omega would be 1 over sine of 1 over capital omega. Now, it turns out that, and 1 over capital omega would be your infinitesimal little omega. It turns out that sine of an infinitesimal is approximately equal to that infinitesimal. So you would have approximately 1 over little omega, which would be capital omega, right? Again, with the reciprocals, and that's in your divergence zone. So that one diverges. Okay, others. All right, well, hearing none, let me give you a couple of these. Well, show you first, I guess I'll show you a little bit of a refinement of these convergence and divergence zones. And then I'll show you a couple of places, a couple of series that can stump the test. So one of the things that you may have noticed is that I had omega times natural log omega in the divergence zone. You can prove that that's in the divergence zone using the integral test. And same with some of these there and some of these others in here. So even between like your omegas times natural logs and your powers of omega that are greater than 1, there are infinitely many of these types of levels in between them, and some are in the convergence zone, some are in the divergence zone. So where this actually has its precise boundary is an interesting question, but one can leave that fuzzy here as to where that actual boundary is. Some of the faculty might or might not know that that these are a part of the Abel-Dini scale that can be used for comparison tests with convergence and divergence. But anyway, here's one, a piecewise defined series. So a series with terms. Actually, that should have been, I should have written that as an infinite series there instead of a sequence. I've got a typo there. So that should be the sum of the a sub n's. If you define your series of where on the non-square terms, you've got your 1 over, let's see, sorry, on your square terms, you've got your 1 over n. On your non-square terms, you've got 1 over n squared. On this one, the level comparison test can't directly figure that one out because sometimes you get 1 over omega, or sorry, you get 1 over a sub omega is omega, and sometimes you get that it's omega squared. And so some of those are in the divergence zone and some are in the convergence zone. So since it's not the same for every omega, depending on whether it's a square or not, then it couldn't tell. So there are some things like that. But here's a more natural one. On this one, the question is whether the sine of n happens to be bigger than 0.6 or less than 0.6, right? If it's bigger than 0.6, then you have a number that here your a sub n would be a constant to the n where your constant's bigger than 1, or otherwise if sine of n is less than 0.6, then it would be less than 1 to a power. And again, those are going to be in different places on your diagram. All right, well, let me go ahead and conclude here. So the magic of the hyperreals is that they give a structure for infinite quantities. So instead of only having a generic infinity, the different rates at which functions grow, your capital omega cubed or 5 to the capital omega or natural log of capital omega, can be specified. The classical methods like the limit comparison test are, in my opinion, essentially less efficient workarounds to get at the same ideas when that specificity isn't available. Now, this level comparison test that I just showed you is nearly universal, and but sometimes other tests can be more convenient. But then instead of a question of finding a test that will work, strategy for testing series becomes more of a question of which test happens to be more convenient. So I realized that I went through a lot of ideas fairly quickly. When I use the hyperreal numbers with my calculus students, it's several days where we're going through like the very beginning portions of it. Like I'll spend an entire class period on approximation, an entire class period before that on levels of numbers, etc. And so I've gone through a lot of these ideas fairly quickly. But it turns out that you can also do or use these methods with hyperreal numbers to find easier and more intuitive methods for finding limits, proving derivative rules, a replacement for Riemann sums, and much more. And if you are curious, then I have a book coming out this fall from Oxford University Press called Calculus Set Free, Infinitesimals to the Rescue. And I invite you to take a look at that book. Faculty members, maybe you want to order that book for your library. This book has been tested in the classroom, both at Union University and at Southern Nazarene University. And the students perform better on limits and certain other items as well using these methods. But anyway, thank you for attending this workshop about the hyperreal numbers. And if anyone has any questions, I'll stick around for as long as we have, but I guess, is there a break? I'm not sure. The next talks, I think, start in about 10 minutes. But again, any questions, I would be happy to answer or talk to you during one of the breaks later.
I had a question in the chat.
Okay, so is there a critical value or series at the separation between divergence and convergence zones? Very good question. I don't really think there is. I don't know absolutely for sure on that, but there's infinitely many levels in between each of these levels in the in our collection of levels of hyperreal numbers. And so I don't know that there's like one at the actual boundary that separates them. If there is, it wouldn't be easy to describe using elementary functions, I don't think. All right, anything else? All right, well, again, thank you all for coming and listening. And I would be happy at any time throughout the day when we're not in talks to chat with anybody that has any questions. But thank you.
Thank you very much, Brian. All right, everyone, in about 9 minutes, we're going to start the second session of student presentations. You'll join those the same way you've been joining all the talks by clicking on the icon in any of the various conference rooms. So I'll be updating the link here in Pythagoras, but that's link is already set up in Euclid, the all hands room and the Hypatia room. So feel free to take a quick break and we'll see you back here in about 8 minutes now.